speaker is Guy Melard. He'll be discussing new results for time-dependent models. Guy, are you here?
You did.
I saw him.
Yes.
I saw him earlier.
Can
Okay,
you hear
awesome.
me? Okay. Well, I will share my screen, please. Where is it? No. Can you see it? Can you see my screen?
Yeah. Yep.
Yes, we can see your
Okay.
screen.
All right.
Proceed.
So I will speak about seasonal ARIMA models with time-dependent coefficients. Like you, Tucker, I will mention seasonal adjustment close to the end. So the idea is to show the potentialities of these time-dependent models, first through a practical analysis and then give the theoretical justifications before the conclusions. There are other ways to deal with time-varying time series, but not only they are rarely used for official statistics, but they are not compatible with seasonality. Here we have proposed a direct extension of ARIMA models with time-dependent coefficients. And to illustrate it, I will show a data set of US industrial production series. And the idea is, I presented that already, at least in the previous versions. And the idea is to first work with a linearized time series, and then we have added a global test on the slopes and stepwise procedure. Here is the definition of a time-dependent ARMA model. The difference is simply adding a subscript T for the coefficients of the AR and the MA polynomials. These coefficients now depend on a vector of parameters, a small number of parameters preferably, and we suppose there are deterministic function of time t and possibly on the series length. And of course, there is support for integrated series. So differences are welcome to cope with trends, etc. And they can be regular and seasonal time-dependent polynomials. Here is an example for TD ARMA 11K. So here, be careful. TD doesn't mean trading day, but well time-dependent. You see here the case of a linear function of time. The denominator here is to keep sure that the coefficient don't grow too much. Otherwise, well, in this case, we have 4 parameters instead of just 2. And the standard classical case is when the slopes phi prime and theta prime are equal to 0. Okay? So the practical analysis will work on US industrial production series. We have worked with series till 2028. And Tramo was used to produce the linearized series and to find the constant ARIMA model, see ARIMA here. And the idea is simply to replace the constant coefficients by a linear function of time. And so after that initial specification of the model, I fit the constant and time-dependent ARIMA models with the same specialized software package. And then the idea is to omit non-significant slopes one by one so that the models are simplified. To make the comparison between these two categories of models, I've used the t-statistics for the TD parameters, so the slopes, also a global test for all the slopes included in the model, and other criteria that are mentioned here, including forecasting. Here are the main information about the series. As you can see, a seasonal difference is present for nearly all the series, and all are include at least one difference. Is it okay? And there are outliers for many of the series. So here are the initial TDR ARIMA models. So you see that about one half of the series, there are 293 series, about one half of them have at least one significant slope. But of course, the SBIC criteria is pretty low because there are numerous unuseful slopes. So by omitting them one by one, we obtain more cleaner models with also about one half of the series with time-dependent coefficients, also according to the global test. And indeed, the results are pretty much better than before, except perhaps the forecasts, which are not that good. Of course, when I speak about significance of the slopes, I should have proposed something behind that. There is no asymptotic theory to justify, for instance, the student or the world global test, except if we are able to prove consistency and asymptotic normality of the maximum likelihood estimators. We have started that in the past, and it is only recently that we have given a rigorous treatment in order to be able, in a paper just published in the Journal of Time series, to deal not only with ARMA, but also with VARMA models. So we can say that the analysis that was just presented is now completely justified. Nevertheless, I should add something, because one of the criteria to avoid numerical problems was to deal with the roots of the polynomials. And in the time-dependent context, this is not so obvious. And this is what I will now present. The theory, as I will show, is based on rather complex assumptions. And the idea is to use an expression for the derivatives of the residuals in terms of the true innovations. And these coefficients, psi, t, I, k, here are used in the assumptions. For example, here I sketched these assumptions. There are conditions here with these coefficients, and there also. Otherwise, we have to suppose existence of moments and existence of an invertible information matrix, of course. Then to discuss this in relation to the roots of the polynomials, I will present here a TD-VAR1 form of the ARMA model, and also MA forms of the residuals and their derivatives. To simplify the expression, I will discuss TD-ARMA 2 model for the equations. And if you go in the literature, you can find arguments already in the book by Lutke Paul. But it was not really fully exploited until now. Here is the equation for TD-ARMA 2, and the idea is to write a vector xt composed of the first two values of the Weber and the first two residuals. And here we have, that can be checked immediately, we have a big matrix that will be denoted capital A T of beta. And it can be seen that here there is the companion matrix of the reciprocal TDAR polynomial. This is, on the contrary, a zero matrix with a first row, which is the same as in the companion matrix of minus the moving average polynomial. And here it's a zero matrix, and there a lower shift in identity matrix. Now, to use this, we need two other matrices, constant matrices. And it can be seen that if you multiply that matrix J to the left to A T of beta, we obtain here a matrix where we can find the companion matrix of the moving average of the moving average polynomial. And the tilde are more complex expression. I will not show that. But if you take all that together, the big vector xt, where the observation, the residual appeared, can be expressed as a moving average with coefficient uppercase psi, given by these expressions, with apparently complex products. To simplify the presentation, I will deal here with constant coefficient. In that case, these products become powers. And so the power of A is written like that, with the power of the companion matrix. And for JA, it has that form with the power of the companion matrix of theta. And because of that, I will not go into the details, but if the roots of these two polynomials at the correct value for beta are greater than 1 over phi, where phi is smaller than 1, then it can be shown that the Frobenius norm of these powers are smaller than a power of k times a constant, and the same can be deduced for the uppercase psi. And more complex expressions appear, of course, for time-dependent models, but the arguments are similar for the time-dependent polynomials. And then when we have that, we can obtain a MA form for the residuals themselves, since the residual appear as one of the elements of the capital X T vector. And we have a similar exponentially decreasing property for the coefficient psi-tk. And the same is true for the derivatives. And so we can indeed obtain the conditions, the more complex conditions that appear in our Journal of Time series paper, together, of course, with the other conditions. What is nice also for those interested in that, it is also valid for Varma models, so Varma and TD Varma models. As a conclusion, we have shown the application of TD ARIMA models to a data set of US industrial production time series. We have seen that in some sense, TD ARIMA models are better justified than constant ARIMA models for many of these series. We had that constraint based on the polynomial roots, which is now completely justified since the roots of these polynomials greater than 1 is a sufficient condition for 2 of the assumption of our paper. Hence, we have a constraint and test completely justified by the asymptotic properties of the QML estimators in TD ARIMA models. What remains now is to add the trading day features and build a seasonal adjustment procedure on top of the time-dependent ARIMA models. Thank you very much for your attention. For those who are interested, I can send them the presentation if they will not be available, and the references are here on the following pages. Thank you again.
Great talk. Thank you. Well, while people think about questions, I'll start off the question. So you had these time series you tested. I was wondering what the sample spans, what the length of those time series were.
So we.
Sorry. So in the beginning of your talk, you tested the time varying the slope coefficients, and what were the sort of the sample spans for those time series? Are they long or short?
Yes.
Yeah, I think it was maybe. I don't remember if it came after this, but you were saying that 50% of the cases.
Yes. Okay. Yes. Yes. Yes.
Yeah. How long were these time series?
These time series were from 1986, I think. It is written somewhere in the presentation, but where here?
Yeah. Okay. Gotcha.
Yes. Some were longer, but so it's a pretty long seasonal monthly time series. Yes.
Yeah. And second question. So I guess you're working on the filtering. Do you have thoughts about how you would do filtering for time dependent?
I don't do filtering. It's deterministic dependency on time only. So there is no. That's why the parameters are the slopes of linear function. Linear functions are the next step after constant coefficients. If you see.
Yeah, but my question is about seasonal adjustment. So, do you have thoughts about how you would do the seasonal adjustment filters when your model parameters are time dependent? That seems tricky to me. It might even be an open problem.
At this stage, there is no seasonal adjustment. As I mentioned at the end here, a seasonal adjustment procedure can be added on top of what I did. For the moment, there is no seasonal adjustment, just ARIMA models, but using the idea behind seeds, it is possible to build a seasonal adjustment procedure by working on the polynomials like in seeds. But at this stage, there is no seasonal adjustment.
Yeah. Yeah, I think it's maybe an open problem. Okay, great. So I see one question in the chat. Can the questioners just unmute themselves, and we have time for maybe a couple minutes for questions. Anna,
yes, I
that's your
see.
hand up. Yeah, go ahead, Anna.
Oh, okay. So
yes, I see the question. I see the question.
I don't see
Is
it.
Yeah, go ahead.
Yeah, I ask you questions, or you have a question in the chat?
Yes, I have a please. I can answer to the question in the chat later in the chat.
Okay,
Yeah,
so
that's fine.
Guy, so excellent talk. Thank you very much. It's a lot to think about the, as Tucker mentioned, the following steps: seasonal adjustment and building an
Yes.
extension of seeds. So it's it's very thought-provoking. I wanted to ask currently what kind of tools do you use to do the estimations, and is it do you have numerical and runtime performance problems with this? Also, are the models, maybe I missed something, are the models predefined, or you have a way of looking for the orders as well? And also, so you said that the linear coefficients were the next step after constant ones. And
Yes.
then so the next step would be maybe a random walk, like in state space, or what do you think about this?
No, I don't believe in random walk for the coefficients. No, to answer your question, I can say that estimation is not a big problem, because I published an algorithm already in 1982 about exact quasi maximum likelihood of time dependent models. But there is no numerical problem. I forgot to mention that it can be also extended to include deterministic heteroscedasticity. And to answer the other question in the chat, the question is in the context of seed, which each component BTD ARIMA. If so, are there interaction between how each component changes model? Yes, I suppose so, but we are not at that stage yet for the moment, since the main paper was published in this year. We have not worked on that until now.
Great.
Yeah.
Thank you. I think we'll move on to our next presenter, but thanks again.
Thank you
Guy.
very much.
That was great.
I will stop sharing. Thank you very much.
Yeah.